So for this part of the lecture, we're just going to do a bit of a recap on differentiation because we're going to be needing it next week as we move on to slightly more advanced differentiation topics. So this might well be something that you can just look through at double speed. But if it's been a while since you did differentiation, then just use this as a chance to kind of remember what's going on. So what is this whole differentiation thing about? Well, it's really about using functions that we've got to find out more about the process that they're modeling. It's all about rates of change. So finding out how fast things are changing over time in particular, but it can also be how things change spatially, depending on what our variables are. So just to remind you, I'm going to move over to Geogebra. And the general idea of what we've got here is we want to see how fast a function changes. So here I've got an absolutely standard parabola here. I think it's y equals x squared. And the kind of question that we'd ask is if our function changes an amount h as x goes from a to a plus h, so I'm moving straight into abstract here, or if I was doing it slightly less abstractly, I would say, okay, if we change our x value from 1 to, well, in this case it looks like it's about 2.2, how much does my y value change? So this particular change in x, what is the change that we get in y? So it's looking at the change in y given a specific change in x. But we do this in a more general setting, so we're just saying, okay, I'm going to take a particular value of x, and I'm going to add, and I'm going to call that a, and I'm going to add a certain amount h to it. So I'm going to get a plus h, and then I find that my function changes from whatever it was when f was equal to a to whatever it is when a is equal to, f is equal, whenever x is equal to a plus h. And the average rate of change over that change in x is given by the change in y over the change in x. So hopefully that's pretty familiar. And the thing that we do when we're thinking about differentiation is we say, well, we really want to know what is the rate of change at this particular point. So we don't want to be looking at the point a and a plus h. We just want to know at a. And the way that we do that is we reduce the size of h. So you'll see as I'm reducing h there, my point b is getting closer and closer. And you'll see that the slope of the secant, so that's the slope of the line between the 2 points where I was figuring out the average rate of change, is getting closer and closer to being a tangent at the point A. And if I was to take h right down to 0, you'd see that I now have this line here. Oops, let me put a pen. This line here is the tangent. Oops, they're not doing a very good job. To f of x at a when we've reduced our h all the way down to 0. So essentially what we're doing when we take the derivative, as we'll see in a moment, we define how we define the derivative. When we take the derivative, we are finding the value of the slope of the tangent at the particular point we're taking the derivative. Okay, so let's just grab an image of that. And we'll pull that into our notes. So over here, there are our image to just remind ourselves. So we know that our average rate of change is the change in y over the change in x. And the way we define the derivative, which is the slope of the function at the particular point f of x, is we say we let the limit as we let the little difference between points go to 0 of our average rate of change. So this limit gives the slope of f of x at x is equal to a. And it's really the slope of the tangent. So that's very hasty. Usually you do that in a couple of lectures. Hopefully it's familiar. If it's been a while, then maybe have a look in a little more detail if you want to at the textbook. But you're not really going to be using this, where we're going to be focusing on using derivative rules. But the idea that you need to take out of this particular bit is that when we find the derivative, we're finding the slope of the function we've taken the derivative of at the point we found the derivative. Now obviously we can do that at a whole bunch of points. So in some sense we're finding a new function when we find the derivative, and that derivative at any particular point x tells us what the slope of the original function was at that particular point x. Okay, so just summarizing what we've got here, the derivative of a given function measures the instantaneous rate of change of the output variable, so that's our y value, with respect to the input variable. Important, when we're actually doing applied stuff, is the units on the derivative are the units of y per unit x. So if, for example, I had a function like this, which was in fact displacement and time in seconds, and our displacement was in meters, so this should look a little bit familiar from physics, and this was my function f of x telling me about the displacement, then f prime of x would be telling me about the speed, and it would be in meters per second. One other thing to note is that we have alternative notation, so we can use f prime of x, but sometimes we want to be very clear about what we're taking the derivative with respect to, in which case we might instead write this as the rate of change of y with respect to x. And next week, when we talk about partial derivatives, when we've got functions of more than one variable, this notation becomes quite important. So hopefully you remember a whole bunch of differentiation rules. Let's just run through them quickly. So if you have a constant function, so you have something like, let's just have a different color. So here's my function f of x is equal to 2, perhaps. Then, so we've got f of x is equal to a constant, then the derivative is equal to 0. Does this make sense? Well, remember, we're looking at the slope of the function, and if you have a look at this function over here, our slope is absolutely flat. It's not going anywhere. So it totally makes sense that we've got that the derivative is equal to 0. Then we have power functions. So any non-zero real number. So this is super general. The only thing that you're not allowed to put in here is 0. Any other real number will do. And then the derivative is n times x to the n minus 1. So for example, if we had, let's have f of x is equal to x to the minus 7, then our derivative will be f prime of x is equal to, so I bring down the minus 7 and I times that by x to the minus 7 minus 1, so that's minus 8. Okay. And then we have sine and cosine functions. The derivative of sine is cosine, and the derivative of cosine is minus sine, so don't forget that. And if you think about it, this kind of makes sense. So I'm going to just draw my sine graph here. So the sine graph is this one. That be f of x, sine of x. Now let's think about what the derivative looks like of this function. So I'm going to expand this a little bit. So what does the derivative look like at the point x is equal to 0? Well, if I draw a tangent line at x equals 0, I didn't do a super good drawing here, but you'd find that's, I mean, it's definitely positive, and it turns out that it's actually equal to 1. On the other hand, if I have a look, so let's just put some points in, we know that that's pi, we know that that's 2 pi, and again, if I look at the point pi, so when x is equal to pi, then it looks like my tangent is probably minus 1. So that was 1, that's minus 1, and by the time I get to 2 pi, I'm at 1 again. Okay, so I've got those points plotted so far. Now let's have a look. If I look at pi over 2, so at this point over here, my tangent is flat. My tangent is equal to 0. So that means that at pi over 2, I must have that my derivative is going through the point y equals 0. And I've got the same thing happening at 3 pi over 2 if I carry on there. So you'll see if I join the points, so I'm going to put them in a slightly different color because I've got too much green going on here. So I would have had this here. If you plotted a few more points, you would see that you're getting the cosine function coming up like that. So that's just to give you a kind of visual clarification that this is true. And if you feel like doing something a little head twisty, draw yourself the graph of cosine, which we kind of got here, and then plot what the tangent is doing, look at the slope at each point, and convince yourself that minus sine of x is the right answer. Okay, so those are our basic function rules, differentiation rules. And those are for specific functions. But now we have some more general. So if we've got something, for example, we've got a constant multiplying a function, then the derivative is just the constant times the derivative of the function. So if, for example, I have a function f of x is equal to minus 16 times x to the 1/3, then this rule says, oh, well, what I've really got is some constant, i.e. minus 16, multiplying this function here. So my derivative must be just the constant, which is minus 16, times the derivative of this function here, which is 1/3 x to the 1/3 minus 1, which is minus 2/3. So if I write that out slightly more clearly, that's minus 16 over 3 times x to the minus 2/3. Okay. We also have the sum rule. So the sum rule says if you're taking the derivative of the sum of two functions, that's just the sum of the derivatives. So you don't have to do anything fancy, you just take the derivative of this bunny and you add it to the derivative of this bunny. The product rule, unfortunately, is not just that we can just multiply the derivatives together. Instead, if we have some function, so I'm going to call it big P, which is the product of function f of x times g of x, then if we take the derivative of our p, what we have is our original f of x times the derivative of g plus our original g times the derivative of f. And you can write this either way around, so it's because we know this is the case, it's the same as saying, okay, we write down g of x, take the derivative of f, and then write down f of x and take the derivative of g. So whichever way around you learned it, that's totally fine. All right, so let's just do a little bit of practice. So here I've got a function f of x equal to cosine of x times x squared plus 2x. And the key thing with differentiation is before you dive in, just spend a little bit of time analyzing and looking at what it is that the overall function looks like, so that you know which rules you're going to be applying. So if I have a look at this function over here, I see that what I've really got is a something times a something. So I'm going to call this bit g of x and this bit h of x. And I see that I've got g of x times h of x, so I know that it's going to be product rule. So if I think about what my result should look like, it should be, this is how I learned to do it, derivative of g times h plus derivative of h times g. Whatever order you want to do this in is fine. Okay, so using that, here we go. So I need the derivative of g, so I need the derivative of cosine of x, and I know that that's minus sine of x. And then I've got to times it by h of x. So I just straight write down. So this bit goes to the derivative of g of x, and here I just straight write down h of x. And then I need to add to that, I need the derivative of h of x. So I need the derivative, so that's going to be 2x plus 2. So that's h of x, and I just write down g of x. So that's going to be times cosine of x. And we're done. So often you'll find with differentiation there are kind of multiple steps happening. And the idea is you need to just focus, be calm, and remember what it is that you're doing and where you start. So, and I should put an f prime of x there because it's not equal to the function. All right, let's have a look at g of x here. So if I want the derivative of g prime of x, so the first thing to notice is that overall I've got a sum. So I'm going to write down the derivative of this first term plus the derivative of what this second term is. Okay, so here we go. Now I know that my variable here is x, so I know that my a's are constant. So I've just got really minus a times x to the 5. So I use my constant rule to say this is going to be minus a times the derivative of x to the 5, which is 5x to the 4. And now I need the derivative of this term over here, which is b, which is also a constant, times x times sine of x. So this is going to be b times, and I'm going to write this out in a lot of detail. As you get better with differentiation, you'll do this in fewer steps, but here we go. Again, using the constant rule, this is going to be b times the derivative of x times sine of x. All right, keeping going, I'm just going to switch the orders here. So I've got minus 5a times x to the 4 plus b times, and now if I look at what I've got for my derivative here, I've got an x times a sine of x. So that's another product rule. So I need to have two terms here. So I'm going to have the derivative of x, which is just 1, times sine of x. And then I'm going to add to that, I'm going to write down my x and take the derivative of sine of x, which is cosine of x. And we could expand this out and neaten it up, but this is fine. So we've got minus 5ax to the 4 plus, now I'm multiplying my b in and getting rid of that 1 because we don't care about b, 1 multiplying things. So I've got b times sine of x plus bx times cosine of x. And we're done. Okay, so if it's been a while, just spend some time practicing these and then moving on to the next rule, which is the chain rule. And the chain rule is really about teaching us how to differentiate functions that have been composed. So you'll notice that what we're dealing with here is some composed function, a composite function, of the form f composed of g of x. So that's why we did composition earlier in this lecture, because just it'll help you remember now when we're doing the chain rule. So what does the chain rule say? Well, I always feel it's not particularly helpful. Seeing examples is helpful, but it says the derivative of this composite function is the derivative of f of g of x with respect to x times the derivative of g of x. So let's just do some examples. So we've got our function cosine of sine of x. So if we were to write this as a composite function, we would say we'd let f of x be equal to cosine of x, and we'd let g of x be equal to sine of x. And then our composite function is f of g of x. So I'm going to work through this in detail, but as you get more familiar with the chain rule, if you haven't seen it before, you'll probably work quite a lot quicker. So we know that the derivative of our composite function is going to be, let's just check what it says here, it's the derivative of f, but evaluated at g of x, times the derivative of g of x. So let's just find some derivatives first. So our derivative of f of x is, well, the derivative of cosine of x is minus sine of x. And our derivative of g of x is the derivative of sine of x, which is just cosine of x. But remember that what we actually need is f of g of x. So that says, well, we need the derivative of f at g of x. So now we need to take our derivative of f, and wherever we see an x, we need to substitute in the g. So here I'm going to have a minus sine of, and instead of x, I need my g, which is sine of x. So putting this all together, what I get is dy by dx, so I'm just changing a little bit of notation here, is the derivative of f evaluated at g of x times the derivative of g of x. So let's put that all together. We need this bit here, so that's a minus sine of x, and I've got to times it by the derivative of g, which is cosine of x. Okay, so that might have been a bit speedy. Hopefully you'll practice this a lot, and you might well find that you don't need to be doing any of this as you go along. But I'm just going to do it again in excruciating detail one more time. So this is why it's handy to have learnt function composition. Okay, so I've got h of x here. It's sine of minus 3x to the 4. So let's break this down into a composite function. So I need my outer function, which is sine. So I've got my f of x is equal to sine of x. And my inner function, g of x, is minus 3x to the 4. Then I need to find the derivative of both of these. So the derivative of sine of x is cosine of x, and the derivative of minus 3x to the 4 is minus 3 times 4x to the 3, so that's minus 12x cubed. But the other thing that I need is I need to actually evaluate the derivative of f at g of x, so I need to substitute in for g of x. So I've got f prime of g of x is cosine of, I'll replace this x with g, so that's minus 3x to the 4. So if I write this all out, my derivative of h is going to be the cosine of minus 3x to the 4 times the derivative of minus 3x to the 4, which is minus 12x to the 3. So just tidying things up a little bit, because it makes my mathematician soul happy, I'm going to move this term to the other side. So I've got a minus 12x cubed times cosine of minus 3x to the 4. Alrighty, so that would be something to practice. We will be using this a little bit, and we're going to need it next week. So please make sure you're feeling good about these rules. Of course, what we also need is some rules for exponential and logarithms, because those are functions that we've been looking at. So here we have for exponential functions, if you have an exponential function of the form f of x is equal to a to the x, then the derivative is just a to the x times the natural log of a. And this leads us to one of the things that I mentioned when I talked about the amazing number e and the exponential e to the x. Let's have a look. If my function g of x is e to the x, and I take the derivative, what do I get? Well, it's going to be e to the x times the natural log of, so I'm base e here, so it's going to be natural log of e, but we know that the natural log of e is just 1. So this is actually just equal to e to the x. So this is the strange thing, that the function y equals e to the x, at every point, the slope of the derivative is equal to the function itself, which is kind of weird. Okay, natural logarithm. If we take the derivative of the natural logarithm, what we get is 1 over x. Be a little bit careful here. Now, the function 1 over x is defined for all values of x except 0. So if I just sketch the function 1 over x, what I get is this thing over here. But of course, remember that our natural logarithm is only defined for x strictly bigger than 0. So what this is really saying is for all positive real numbers x, the derivative of the natural log of x is 1 over x. And then we end up with this, rather than both parts there. It's not enough, obviously, to just be able to take the derivative of the natural log. We need to be able to take the derivative of any log, and it looks very similar. So if we've got log base b, then the derivative is 1 over x again, but we've got it times natural log of b in the base. Let's do a little bit of practicing. So I want to differentiate e to the x squared with respect to x. So here we're looking at this and we go, this is a composite function. So I've really got some f of x, which is e to the x, and a g of x, which is x squared. And if I take the composition, I get e to the x squared. Looking at the derivatives of these, I take the derivative of f will give me e to the x. If I take the derivative of g, that will give me 2x. And so putting it all together, I get dy by dx is equal to, well, it's the derivative of f, but evaluated at g of x. So that's e to the x squared times 2x. Okay. Now let's have a look at part b. Again, we've got a composite function. Here our outer function is log base 10 of x, and our inner function is cosine of x squared, and we realize that actually this in itself is a composite function. So we're going to take this step by step. Let's just get that far. So if we take the derivative of f, we're going to get 1 over x times the natural log of 10. And now let's think about taking the derivative of g. Now g has its own composite function. I'm going to call it, this is really f bar, so that's a different f, or let's rather call it f1, which is the cosine of x, and g1, the inner function, which is x squared. So if we look at the derivative of this, we've got the derivative of f1 is minus sine of x, and the derivative of g1 is 2x. So the derivative of g of x is going to be this derivative evaluated at g1, so that's minus sine of x, except we replace the x with x squared, times the derivative times, which is 2x. Phew. Okay, so what we've got is we've found the derivative of f, which is this bunny over here, and we need to remember we evaluate that at g, and we found the derivative of g. So we can put this all together and say the derivative of f of x is equal to derivative of f evaluated at g. So I'm going to do this as a 1 over natural log of 10 times 1 over g. So g was cosine of x squared. And now I've got to times it by the derivative of g, which is this thing over here, times minus sine of x squared times 2x. Okay, so there's a lot going on there. And we could tidy this up a bit. We could have minus 2x times the sine of x squared all over natural log of 10 times cosine of x squared. Okay, so that was pretty speedy. Again, spend some time getting used to it if it's been a while. So that was all the technical stuff, and it is a bit of a pain, but you just gotta learn it. It's like learning vocab for a new language. Just spend some time getting happy taking derivatives of functions. But why we care about this is we'd like to know what is the use of the first derivative. Well, think about what we're usually doing when we have a function. We have a function modeling some process, some data that we've got, and we'd like to find out more about that data than we can by just looking at the numbers. So the very first thing that the derivative can tell us, if our derivative is modeling our data, is our data increasing or decreasing? Because we know that if we have a function, for example, doing something like that, anywhere you take the tangent line, so any tangent line that you draw here, is going to have a positive slope. So we know that this function is increasing. So this tells us that if we make an increase in our independent variable, then our dependent variable will increase as well. So that's kind of useful. And similarly, if we have some function doing this, no matter what kind of crazy shape it's got, anywhere that I take a tangent here, it's going to be decreasing. So this tells me that if I increase my independent variable, then my dependent variable is going to decrease. Okay, so that's kind of useful. But in fact, we get more information about this because it doesn't just say, oh, it's getting bigger or oh, it's getting smaller. It tells us the rate. So when we actually substitute values for x into our derivative, it tells us how much. So if we put, for example, let's have f of x is equal to x squared at example x equals 2, our first derivative is 2x, so evaluating at the point x is equal to 2 gives us an actual numeric answer. So this tells us that when x is equal to 2, f of x is increasing by 4 units, for every 1 unit increase in x. So this tells us this is quite a steep increase. We make one little change, one step change in our x, and we get a 4-unit change in our y. And similarly, if you were doing something that had a negative derivative, you'd know how much you were decreasing. So it gives you a sense of, is this thing increasing really, really rapidly or really, really slowly? And then the other pretty useful thing is it tells us where our function has maxima and minima. So this is really important. So there are kind of, and the key here is noticing that if I have a function that has a maximum, at the maximum, my first derivative is equal to 0. Similarly, if I have a minimum, then my first derivative is equal to 0. Now it's not quite that simple, because I could also have a function that does this, or maybe does this, and at both these points as well, my first derivative is equal to 0. So you can't just say, oh, if my first derivative is 0, then I have a maximum or minimum. But notice that the key thing that we have here is if we've got a maximum, then if we look slightly to the left, so if we look to the left of where our first derivative is 0, our function is increasing, so our first derivative is positive. But afterwards, our first derivative is negative. The opposite happens when we have a minimum. So for a minimum, to the left of where we have our flat derivative, we have that the first derivative is negative. So I should really put greater than 0, less than 0. But afterwards, we have that the first derivative is greater than 0. But in the cases where we don't have a maximum or a minimum, notice that our first derivative stays the same. So in this increasing case over here, here's our first derivative is equal to 0. But on both sides of this, our first derivative is bigger than 0. And in this case, on both sides of our flat bit, it's less than 0. So we can use these criteria to find out where our functions have maxima and minima. And that's pretty important because you're going to want to know the maximum size that something could reach, or the highest point that a ball flies as you toss it up, things like that. So there's a lot going on with the first derivative. But that's not all. So remember, if you take the derivative of something, you end up with a new function. So if we look at the things that we found the derivatives for here, for example, so we took the derivative of y is equal to x squared, what we got was a new function. So our example here was y is equal to e to the x squared, and our derivative was 2x e to the x squared. So this in itself is a function, and there's no reason why we can't take the derivative of that. So if we take the derivative, what we end up with is the second derivative, which we indicate like this. And we use exactly the same rules. So if we were to do that over here, we'd say, okay, well, I've got a function times a function. So it's going to be product rule. So I'm going to take the derivative of the first part and multiply it by the second part. And now I'm going to write down the first part and take the derivative of the second part, which I know is 2x e to the x squared. And tidy this all up a little bit. We get x e to the x squared, and that should be a plus. Sorry. 4x squared e to the x squared. And if you felt like it, because if you have a look at this over here, you can see that that's a function, so you could take the derivative, that would give you the third derivative. You can keep going. As long as you can keep taking derivatives, you can keep taking derivatives. But often it's the first and second derivatives that we really use when it comes to looking at functions and how they work. So the question is, what use is the second derivative? Well, it is the first derivative of the first derivative. So it tells us the same information about the first derivative as the first derivative tells us about the original function. So our first derivative, remember, tells us about the slope of the graph. So our second derivative tells us if our slope is increasing or decreasing. So it tells us if our function is getting steeper or less steep. Or if we're thinking about a decreasing function, is it decreasing but getting, so it's negative but getting less negative, or is it negative and getting more negative? These are things that the second derivative tells us. And exactly like with the first derivative, it's not just saying it's getting steeper or it's getting less steep, it's actually giving the rate. So if you evaluate our second derivative, it tells you the rate at which the slope is increasing or decreasing. What this all really boils down to is saying, where is our function concave up or concave down? So concave up is if a function looks like this, or a combination of those two. So that's concave up. And this is when our second derivative is positive. Or rather, let's write this. Okay, so you can see what's happening here is in each case, our first derivative is increasing. Now it seems weird because you'll have a look at this one and go, but that's decreasing. Our first derivative is negative, but it's getting less negative. So if you were to plot it, you would have something that started very negative and then gradually got more and more positive. So it is actually increasing. On the other hand, what does concave down look like? Well, it's anything that looks like that, or the combination of the two. And we know that this is happening when our second derivative is negative. So what you'll notice is that two cases are things that we've looked at before, where we're looking at maxima and minima, and this gives us another way of finding out if a point where our first derivative is 0 is a maximum or a minimum. So if you find that your first derivative is 0 and your function is concave up, then you know that that's a minimum. Similarly, if you see a point where your first derivative is 0 and you find the second derivative and you find that it's negative, then you know that you've got a maximum. Okay, so that's it for recapping derivatives. Please spend some time. There are quite a few questions on the quiz about this. We will be carrying on using this next week. So please, make sure that it's rock solid. All right, there we go. End of the content for week 2. Well done.